Alright. Alright. What are we doing? What's going on? Ooh, had a day. I have had a day. What are we doing? We are probably going to be continuing the Rust, running through the Rust book at chapter 4. I did a little bit of chapter 4 on my off time. Didn't get quite far enough in it to justify not just starting chapter 4 over. Why not? We can still keep going on chapter 4. Let's... Ooh. Was YouTube telling me that things didn't look so great? What was that? Alright, well... Let's go over to the new screen. I've decided the whole, bring in a fancy animation for the documentation window and then bringing it out. Probably not the best idea. Probably best to just go with what was working before. Just put them side by side. Was dedicating entirely too much time to that stuff. So now, let's see what the ownership feature in Rust is about, where we actually own variables? What does it mean to own a variable? So, intro to the chapter, ownership in Rust. Ownership is Rust's most unique feature, has deep implications for the rest of the language. It enables Rust to make memory safety guarantees without needing a garbage collector. Just to... Actually... Whoop. See how that looks. There we go. So this is kind of what I was doing for a little bit. Some examples that I was writing down from the Rust book. I was kind of working through them. Let's go ahead and create another window too. Ship. Got it. Cargo run. Aha. All right. So, we enable the Rust to make memory safety guarantees without needing a garbage collector, unlike Python. So it's important to understand how ownership works. So I think what a lot of the point there is, it's hard to grasp the rules by which the garbage collector actually works in those languages, like Python, like the garbage collector, and how that stuff works in languages like Python and Java and whatever else has garbage collectors. Hanny, I'm using the superior development environment, which is Vim and Tmux, or specifically NeoVim. But hey, let me just. I'm always gonna be tweaking, aren't I? Always gonna be trying to get things a little bit more. How about you guys sit over there? Sit right there. So, yeah, just there's a lot to having, like, here is a set amount of rules to yeah. And yeah, oddly enough, it's not gonna look like, it doesn't actually look like that on my screen. For whatever reason, I thought it was neat that OBS actually respects my terminal's transparency. I'm like, wait, why would it respect my terminal's transparency? But that's cool. That means I can put whatever background I want to this rather than just my wallpaper. You guys don't get to see my wallpaper. You get to see the animated background, which is even cooler. I kind of wish I had that as my background, but anyway. So, Rust's most unique feature, deep implications. It's important to understand how ownership works. This chapter will talk about ownership as well as several related features, borrowing, slices, and how Rust lays data out in memory. Those of you familiar with the stack and the heap are going to have a good time today, because it gets real. It actually kind of explains, like, how is a string stored? So, we start off. Ownership is a set of rules that govern how a Rust program manages memory. All programs have to manage the way they use a computer's memory while running. Some language have garbage collection that regularly looks for no longer used memory as the program runs. In other languages, the programmer must explicitly allocate and free the memory. Rust uses a third approach. Memory is managed through a system of ownership with a set of rules that the compiler checks. I kind of like this. Maybe the ownership stuff, I'm still wrapping my head around. But I like the idea that memory is freed, not by you actually calling free explicitly, but here is a hard set of rules. Memory, once this variable is done, it is gone and dead, and that memory is freed up. Fuck you. And if you can't deal with that, skill issue. So that's kind of neat. If any of the rules are violated, the program won't compile. Skill issue. None of the features of ownership will slow down your program while it is running. All right. So because ownership is a new concept for many programmers, it does take some time to get used to. There's good news, and that the more experienced you become with Rust and the rules of the ownership system, the easier you'll find it to naturally develop code that is safe and efficient. Keep at it. Yay, hooray. When you understand ownership, you'll have a solid foundation for understanding the features that make Rust unique. And we're going to use a data type that is very common, that most people understand, and that's strings, to kind of give us examples. So the stack and the heap. For those people who don't understand the stack and the heap, such as Java programmers, no, JavaScript programmers. I almost didn't even want to say it. That's JavaScript programmers probably don't really grasp the stack and the heap all that much. They don't have to, but that also means that they don't. Many programming languages don't require you to think about the stack and the heap very often. So basically, I'm going to kind of zoom through this. There's basically two different kinds of memory that you have in your RAM, let's say. And I'm not talking about like your L2 cache, L3 cache. When you think of putting something into memory, you are storing something in your computer's RAM. But there's really two types of RAM that you have, and that is the stack and the heap. The stack is almost exactly what it says. It is, you put something on the top of the stack, and it is there, and you have a fixed amount of data. But it's also a sort of first in, first out system, or last in, first out, LIFO. It's not really good for dynamic allocation, where it's like, oh, you want to append, if you have a list of things and you want to append to the list. It's not really good for that. What you're really looking forward to is the heap. The heap is good for a lot of like, oh, I don't know exactly how much memory I need, and I may know how much memory I need now, but I might need more later, I might need less later. So the heap is really good for that. And spoilers, something I learned the other day reading through this book, the way Rust stores strings, I don't know how other languages store strings. I don't know how Python stores strings, but turns out Rust actually uses both the stack and the heap to store specific string data. I believe there's a couple different ways that you should be able to store strings. A couple different types that eventually call themselves strings. but you get to use both, the stack and the heap. All right, so let's go to the ownership rules. First, let's take a look at the rules. Keep these rules in mind as we work through the examples that illustrate them. Each value in Rust has an owner. There can only be one owner at a time. When the owner goes out of scope, the value will be dropped. So we have variable scope. Now, I haven't been fond of the verbiage that they use for variable. To me, in my programming career, I've always thought of the variable as the complete unit. They separate the notion of a variable's name and a variable's value. And these are two distinct things, but for whatever reason, they've decided that the name of the variable is now called the variable. If you hear me, I might mentally say, hey, I might remind you or say like, okay, don't think of the variable, think of the name of the variable. When the book says variable, it is probably either referring to both the name and the value, or it might just be referring to the name. So I will try to make the distinction. Here is the name. Here is the value. Now that we're past basic Rust syntax, we won't include all the fn main bullshit. So if you're following along, make sure to put the following examples inside something that actually gets called if you try to run the program. As a result, our examples will be a bit more concise, letting us focus on the actual details rather than the boilerplate code. As a first example of ownership, we'll look at the scope of some variables. A scope is the range within a program for which an item is valid. Take the following variable. So let s equal hello. So we have that in our main here. I'm going to go ahead and highlight it for you guys to see. I've underscored it because if I don't underscore it, there's a nasty habit that my compiler tells me that, oh god, this is a thing. It's like, oh, it's unused. So my compiler yells at me with warnings. So what I've done is I've named it _s, which gets the compiler and the rules checker and the linter to just ignore that. It's okay for that to not get used later because I'm just doing fun things. So we say let s equal hello. The variable name s refers to a string literal, where the value of the string is hard-coded into the text of your program. So we took the name and the value, and we've created a variable s. Variable is valid from the point at which it's declared until the end of the current scope. Listing 4.1 shows a program with comments annotating where the variable s would be valid. So if you see, there's my squirrel brackets, curly brackets. I think they're called braces in some parts of the world. I don't know. I haven't been to them. But everything inside of the curly brackets says this is a scope. It doesn't even have to be a function. It is a scope. I think in Python it'd be just called a block of code. But everything in the block is considered a scope. So, in fact, and there's comments here, which I've copied over from the book. Here is the scope. S is not valid here as of yet. We haven't even, in fact, I should modify it for that. S is not valid here because we haven't declared it. So then we declare it on this line. We say S is now valid because we've declared it and we set the value to hello. And in theory, we could have been doing stuff with it. We could have been print lining it. I think it's, I think that's what you do there. Not find value S in this scope. In fact, I should rename it _s. So we say do stuff with S. I'll just do stuff with S. Save it there. And then we close this block of code, which then deallocates the which then deallocates _s, and we can even try that. We can experiment a little bit with it. After block. And then we save it, and we already have my compiler yelling at me, my linter, saying, "You can't find it in this scope. It doesn't exist. It's already dead. He's already dead, Jim. Get the fuck out of here with that. There's no _s doesn't exist. So don't even bother running that code." And then at the end of the squirrely bracket there, scope is now over. S is no longer valid. Got it. Which now, let's go through all of this. Basically, that's what I pointed out. Variable in the scope in which it's valid. In other words, there's two important points in time here. When S comes into scope, it is valid. So basically right here, when S got declared, and then it remains valid until it goes out of scope, which at this line, the scope is over. We're done with it. The relationship between scopes and variables and when variables are valid is similar to that in other programming languages. We will build on top of this understanding by introducing the string type. To illustrate the rules of ownership, we need a data type that is more complex than those we covered in the data types section of chapter 3. The types that covered previously are of a known size, can be stored on the stack and popped off the stack when their scope is over. And they can be quickly and trivially copied to make new, independent instance if another part of code needs to use the same value in a different scope. But we want to look at data that's stored on the heap and explore how Rust knows when to clean that data up. We'll concentrate on parts of the string that relate to ownership. These aspects also apply to other complex data types, whether they are provided by the standard library or created by you. We'll discuss string in more depth in chapter 8. So we've already seen string literals, where string value is hard-coded into our program. String literals are convenient, but they aren't suitable for every situation in which we may want to use the text. One reason is that they are immutable. Did I say immutable in that last sentence? Mistakenly? Because I read it? Whatever. Another is that not every string value can be known when we write our code. For example, what if we want to take user input and store it? For these situations, Rust has a second string type, capital S string. This type manages data allocated on the heap and as such is able to store an amount of text that is unknown at compile time. You can create a string type from a string literal using the from function, like so. So we have let s is equal to string from hello. So we instantiate an actual data type string from a literal string of hello. I imagine I think there is an interesting question of like, does let t equal hello? Like, is that just a shorthand for this? Is this line a shorthand for this line? I'm interested in knowing that. I guess we'll probably figure that out later. Or we could, I forgot what was the way to actually print out data types. The type of an instantiated piece of memory. Anyway, so the double colon operator allows us to namespace. So the namespace in this case is string. This particular from function from under the string type rather than using some sort of name like string from. We'll discuss this syntax more in the method syntax section of chapter 5. When we talk about the namespacing with modules in paths for referring to an item in the module tree in chapter 7. So this kind of string can be mutated. So I already have let mute s. So I called it t in this case. We do t push string world, push string appends a literal to whoever. And then we do print line. So here I've said let mute t is equal to string hello, and then comma, we add comma world by using push string, and in fact t dot push string appends a given string slice onto the end of this string. Thank you for that from my linter. And then we print that out. There's the formatting. I wonder, can I do this? Is this also valid? I forget. Is there a reason it would yell at me? No, it's not going to yell at me. Hooray. So now we're going to go on to... Oh, hang on. What's the difference here? Why can string be mutated, but literals cannot? The difference in how is in how these two types deal with memory. So I'm pretty sure, before we go forward, that it has something to do with the fact that string literals aren't even actually stored in memory or in memory or the stack or the heap. String literals are stored inside of the program. And once they're inside of the program, then you instantiate it into memory, and then it needs to have to worry about it. But as a string literal is stored in the program, yes, it's in memory. The program's in memory. Shush. But a literal doesn't have to worry about any of that. But it's best if a literal doesn't have to. A literal doesn't have to worry about that. What am I trying to say? You don't want to have any concerns about fucking with your literals. Let's just say that. Oh, here we go. In the case of a string literal, we know the contents at compile time, so text is hard-coded directly into the final executable. Yeah. This is why string literals are fast and efficient, but these properties only come from the string literal's immutability. Unfortunately, we can't put a blob of memory into the binary for each piece of text whose size is unknown at compile time and whose size might change while running the program. With the string type, in order to support a mutable, growable piece of text, we need to allocate an amount of memory on the heap, unknown at compile time, to hold the contents. This means the memory must be requested from the memory allocator at runtime, and we need a way of returning this memory to the allocator when we're done with our string. That first part is done by us. When we call string from, its implementation requests the memory it needs. This is pretty much universal in all programming languages. However, the second part is different. In languages with a garbage collector, the garbage collector keeps track of and cleans up memory that isn't being used anymore, and we don't need to think about it. In most languages without a garbage collector, it's our responsibility to identify when memory is no longer being used and to call code to explicitly free it, just as we did to request it. Doing this correctly has historically been a difficult programming problem. Ain't that the truth? If we forget, we'll waste memory. And even the White House doesn't want you wasting memory, guys. You know, the White House says we need to think about memory safety. If we do it too early, we'll have an invalid variable. If we do it twice, that's also a bug. We need to pair exactly one allocate with exactly one free. Anyone who's familiar with the C language has all kinds of fun with that. Rust takes a different path. The memory is automatically returned once the variable that owns it goes out of scope. Something in my eye. Here's a version of our scope example from 4.1 using a string instead of a string literal. So I believe I have that written down here. I called the function main2. S comes into scope. S's value moves into the function. Oh, okay. No, that comes later. But we'll call this let r equals string from, Is it from stir? Or no, it's just from. Okay. From. And then we say it converts to this type from the input type. Just call it hello. But then we'll surround it with scope stuff. Oh, nope. At the linter, there we go. And it doesn't like that it's not. There we go. So R is now valid. Do stuff with R. R is no longer valid. So scope is now over and S is no longer valid here. S is valid from this point forward. Yep. There is a natural point at which we can return the memory to our string needs to the allocator. When S goes out of scope, when a variable, sorry, there is a natural point at which we can return the memory our string needs to the allocator, and that is when S goes out of scope. When a variable goes out of scope, Rust calls a special function for us. This function is called drop. Let's go ahead and open a tab and look at all this look at all this drop. There's a lot of documentation on drop. So required methods drop. Drop executes the destructor for this type. This method is called implicitly when the value goes out of scope and cannot be called explicitly. However, the memDrop function in the prelude can be used to call the argument's drop implementation. All right. There's a natural point. Oh, I already read this. Rust calls drop automatically at the closing curly bracket. In the C++ pattern, this pattern of deallocating resources at the end of an item's lifetime is sometimes called RAII, or Resource Acquisition is Initialization. The drop function in Rust will be familiar to you if you've used RAII patterns. This pattern has a profound impact on the way Rust code is written. It may seem simple now, but the behavior of code can be unexpected in more complicated situations. When we want to have multiple variables, use the data we've allocated on the heap. Sorry. It may seem simple now, but the behavior of code can be unexpected in more complicated situations when we want to have multiple variables. Use the data that we've allocated on the heap. Let's explore some of those situations. So we have variables and data interacting with move. Move is very interesting. Multiple variables can interact with the same data in different ways in Rust. Let's look at an example using integer listing 42. Using an integer listing 42. So we instantiate an integer named x, and we give it the value 5, and then we instantiate an integer y, and we set it equal to x. We can probably guess what this is doing. Bind the value of 5 to the variable name x, then make a copy of the value in x and bind it to y. We now have two complete variables, x and y, both equal to 5. This is exactly what's happening because integers are simple values with a known fixed size, and these two 5 values are pushed onto the stack. Oh, that's not the diagram I was thinking of, but basically, two separate instances of the number 5 now exist in memory. One of them is owned by the name of x, one of them is owned by the name y, but there are two instances of the number 5. So now let's look at the string version. Let s1 equal string from hello, and let s2 is equal to s1. This looks very familiar, so we might assume that the way it works would be the same. That is, the second line would make a copy of the value in S1 and bind it to S2. That's not quite true. Take a look at the next figure to see what is happening to the string type under the covers. Ooh, getting fancy, getting spicy here. Going under the covers with it. A string is made up of 3 parts, shown on the left. A pointer to the memory address that holds the contents of the string, a length of the string, and a capacity. I don't know what capacity is. I kind of wish I knew what they meant by capacity. This group of data is stored on the stack. On the right is the memory that holds the contents. So here's our diagram for S1. If I can I zoom in on it? Can I zoom? There we go. Flashbang for you guys. So S1, there is, I don't have capture cursor on, but on the right side of the arrow there, you have the actual ASCII text of HELLO, and those are stored over there. But then, how do you know where that is in memory? Well, you actually have S1 stored in the stack rather than the heap. And the S1 is really the pointer, and the pointer tells you where the HELLO is. The length says that HELLO is 5 characters long, and then the capacity says something. I don't know what it says quite yet. We're probably going to figure that out later. The length is how much memory in bytes is the contents of the string. I can read it, but I don't know if you can. Here we go. The capacity is the total amount of memory in bytes that the string has received from the allocator. That's right. I forgot. Because HELLO in ASCII, that's 1 byte, 2 bytes, 3 bytes. But if it's in Unicode, every piece of text in Unicode is like what? 5, 6 bytes? It's crazy. And that's how emojis exist, and other languages. The difference between length and capacity matters, but not in this context, so blow it out your ass. When we assign S1 to S2, the string data is copied, meaning we copy the pointer, the length, and the capacity that are on the stack. So this line actually got me, and I'm really curious. If you are calling stuff on the stack, or if you are copying data types that have stuff like this, where you have the length, the pointer, the length, and the capacity, and you have like metadata rather than the actual data, and the metadata is on the stack, if you're copying that, I'm guessing that anything that stores both in the stack and the heap, if you are copying, the stack data gets copied, but I don't know if that's true in every case for stuff like copying. In other words, data representation looks like figure 4.2. So the heap never gets copied. The heap, there's only one instance of HELLO. But S1 and S2, there's 2 instances of pointer to index 0, pointer to index 0. There's 2 instances of length 5, and there's 2 instances of length capacity, or capacity 5. But there's only one instance of HELLO. That's really cool. Now, you can still do it the other way, where both the stack and the heap get copied, and you have 2 instances of HELLO. But let's read this and see what's up. The representation does not look like figure 4.3, which is what memory would look like if Rust instead copied the heap data as well. If Rust did this, the operation S1 is equal to S2 could be very expensive in terms of runtime performance if the data on the heap were large. Earlier, we said that the variable goes out of scope. Rust automatically calls the drop function and cleans up the heap memory for that variable. Figure 4.2 shows the data pointers pointing to the same location. Which one is 4.2? Yeah, this one up here, the one that's center of the screen. It shows both data point at the same location. This is a problem. When S2 and S1 go out of scope, they will both try to free the same memory. This is known as a double free error and is one of these memory safety bugs we mentioned previously. Freeing memory twice can lead to memory corruption, which can potentially lead to security vulnerabilities. To ensure our safety, after the line S2 equals S1, Rust considers S1 as no longer valid. Therefore, Rust doesn't need to free anything when S1 goes out of scope. Check out what happens when you try to use S1 after S2 is created. It won't work. So where did I put that in here? I think I put that in here somewhere. I didn't. Okay. So let's just make a main 3. And we'll say let S1 equal to string from hello. And then we say let S2 equal to S1. We print line S1. We say that, and oh man, how many problems has my compiler just told me that there exist here? So borrow moved value of S1, value borrowed here after move. Okay. Value borrowed here after move. Consider cloning the value if the performance cost is acceptable. Value is moved here. We're getting a warning. Unused variable S2. Let's just go ahead and change that. Okay, so we got rid of some variables. Borrowed value of S1. Value moved here. Move occurs because S1. And then there's the error. Borrow of moved value S1. Value borrowed here after move. Let's just go ahead and go into that. See? And it already tells us, no, don't mess with me today. The compiler is now saying value is borrowed after move. So we're probably about to learn about what a move is. Take a little sip. To ensure memory safety. Okay, you'll get an error like this, which we did, because Rust prevents you from using the invalidated reference. So let's go back to our code and let's just get rid of main 3 entirely. If you heard the terms shallow copy and deep copy while working with other languages, the concept of copying the pointer length and capacity without copying the data sounds like making a shallow copy. But because Rust also invalidates the first variable, instead of calling it a shappy collie, it's a shappy collie, ladies and gentlemen. That's what we're doing. We're shappy collieing things. Why does that sound filthy? I don't know. I don't know if I like the sound of that. But instead of it being called a shallow copy, it's known as a move. In this example, we would say that S1, the value that was pointed to by S1, was moved into S2. So what actually happens is shown in figure 4.4. I don't know if I like this diagram so much because all it does is take the S1, I guess we can call it the metadata, the stack metadata of S1, and then it darkens it. What's really happening is that it's no longer valid, and I guess I'm gonna guess that the data on the stack is freed up, and it's popped out, and it's just like, no, we're not worried about that. We're just getting rid of it. So that solves our problem. With only S2 valid, when it goes out of scope, it alone will free the memory, and we're done. In addition, there's a design choice that's implied by this. Rust will never automatically create deep copies of your data. Therefore, any automatic copying can be assumed to be inexpensive in terms of runtime performance. So anytime you call like a copy or like instantiate a new thing by calling it the old thing. In fact, anytime you do something like this, it's telling you, hey, we're only copying the metadata and putting it on the stack. The actual variable in memory, the stuff in the heap, is just getting pointed to again by something else. So that's where that goes. copy that and cargo run. A local variable with a sim. Oh, I didn't call it S2. There we go. It does run. Function main3 is never called. Let me just... There we go. So in main3, we just say hello from the main3 function that demonstrates stack. I did that. Nope, still didn't like it. I like that it's going past line column 79 there. I don't like that. Ah, well. So, variables and data interacting with clone. If we do want to deeply copy the heap data of string, not just the stack data, you can use a common method called clone. We'll discuss this method in method syntax in chapter 5, but because methods are a common feature in many programming languages, you've probably seen them by now. So we let s1 is equal to string from hello, and then we clone that into s2, and then we just say, fuck it, let's print it. So do we have makes copy, some integer, some integer. Let's just call this main4 then. Nothing there. Demonstrating the clone effect copies both stack metadata and the heap data of a string. So we let s1 equals string from. Oh. No. Hello. And then we say let s2 s1.clone. And let's print line of both of these. And then it says S1, S2. I'm going to do it this way because I'm a gangster. Main4 is never used. S1, S2. Neighbor from main4. Then we'll go back up here, call that. We'll run it. Hello, hello, neighbor from main4. There we go. That's fun. This works just fine and explicitly produces the behavior in 4.3 where the heap data does get copied. When you see a call to clone, you know that some arbitrary code is being executed and that code may be expensive. It is a visual indicator that something different is going on. Oh, here we go. Stack only data copy. There's another wrinkle that we haven't talked about. This code using integers, part of which was shown in 4.2 and works and is valid. So we say let x equal to 5, let y equal to x, and then we print both of them. This code seems to contradict what we just learned, that we don't call clone, but x is still valid and we don't, and wasn't moved into y. I'm gonna go ahead and run through this real quick and say the reason that's the case is because x and y aren't strings, and because they're of a known length, we know exactly how much data they take up in memory. There are certain data types that are called scalars that exist at a fixed length. We know how much memory they take up. They don't grow or shrink. So we just put it on the stack, which means we don't have a problem actually copying the stack data again. and putting the data on the stack a second time. So we clone that out, and it's all fun. So, and then the book says there's a whole bunch of integer types. There's unsigned 32, the Boolean types where you can either have true or false, the floating point types such as, like 64-bit floating, the single character type, which always only takes up 1 byte because character is meant to be ASCII. And then we say tuples, which are basically lists, but at a defined length, if they only contain types that also implement copy. So for example, they are I32, two 32-bit integers that's still a fixed length in memory. Oh yeah, also, Rust won't let us, so the way they define that, something that's a scalar, is that it has to implement a function called copy, or a trait called copy. So which I think means everything goes on the stack and is a fixed length. But yes, if the type or any of its parts has implicated the drop trait. So hang on. Actually, I'm going all the way back. There's a special annotation called the copy trait that we can place on types that are stored on the stack, as integers are stored on the stack. If a type implements copy, they don't move, but are just copied onto the stack again. Now, this also means that they don't implement drop, which means they don't go out of scope. And the type needs we add the copy annotation to that type, we'll get a compile time error. So that's a thing that's going to be fun for the future. Anyway, ownership and functions. Here's where ownership gets kind of weird and funky. The mechanics of passing a variable to a function are similar to those when assigning a value to a variable. Passing a variable to a function will move or copy, just as assignment does. Listing 4.3 has an example with some annotations showing where variables go into and out of scope. So let's make a new main. We'll just call it then main pass to function. Now we have let s equal string from hello. And we already have takes ownership and let x equals 5. So we'll just call takes ownership. And that'll be s. And then after takes ownership, we let x equal 5. And we say makes copy of x. I'll get rid of that line too. So that actually already exists up here in main 2, I think. Yes. So we let s equal string from hello. We take ownership and s's value moves into the function and technically is no longer valid here. So we could try and print line s. And the compiler doesn't like it because we actually already moved it into the other scope. But because we moved it in the other scope of it taking ownership, because we have our curly brackets here, everything that's in curly brackets is a scope. Once the function exits, the scope is gone, which means some string is now deallocated. Hang on. Consider cloning the value if the performance cost is acceptable. Consider changing this parameter type in function takes ownership to borrow instead if owning the value isn't necessary. We'll get to borrowing later. But short version is we've now moved s from outside of one scope into another scope, and once that scope completes, we actually deallocate s. So we get rid of the metadata and the value. So s no longer exists after this line because it goes into a new scope. which is a weird thing to work with, but I guess you kind of just have to. Oh, I should probably... Oh. There we go. Function main pass into function is never used. Main 2. Main pass into function. Everything looks good still? Yep. Cargo run. Got it. So now, if we tried to use S after the call to takes ownership, Rust would throw a compile time error. These static checks protect us from mistakes. Oh, my jaw hurts. Talking again. So we throw a compile time error. The static checks protect us from mistakes. Try adding code to main that uses S and X, which we already did. I just showed you, to see where you can use them and where ownership rules prevent you from doing so. Return values in scope. Returning values can also transfer ownership. Listing 4.4 shows an example of a function that returns some value with similar annotations as those in listing 4.3. Okay, so now let's say fn main return from, oh, nope, from function. So we have let s1 equal gives ownership. Nope. So we have s2 and no. s3. s2, we're going to say string from below. And then s3 is takes and gives back of s2. So we have gives ownership, moves its return value to S1. Save that. There we go. S2 comes into scope. S2 is moved into scope or gives ownership. Oh, sorry. Moved into ownership, into scope for takes and gives back, which then moves its return value into S3. Oh, that's the problem. Okay. None of you will know this because I wasn't writing code on, I wasn't streaming the code for something I was writing earlier, but I was running into a lot of problems trying to pass in this variable and trying to get it back. It's like, okay, so if it dies there, what do I do with it now? So I was struggling with the idea of like, oh, does it borrow it? And I need to move this data into here, and the whole like wrapping that was one of my big problems. So we are in now territory that I haven't seen yet in this book. Let's say gives back, which then moves its value to S3. And then after that, which then, sorry. Let me, just for sake of funsies, and then S3 goes out of scope, it's dropped. S2 was moved, so nothing happens. This one goes out of scope. So now we actually have to write fn gives gives ownership, which should return a string type. Let some string yours, and then we return some string. Fn takes back and it takes in a function string, which is a string type, and it should return a string. Nope. There we go. Oh. Too much space there. There we go. So there's let some string. Which means string from, oh no, takes and gives back is return a string. Never used. So you have takes and gives back. Let's gives ownership, so we return gives ownership and takes and gives back. Wait. This function creates a new variable, gives ownership to its, gives ownership of that variable to its caller. Actually, I should. This function. This function takes ownership of the variable it's called with, but then it returns it, giving ownership back to, not giving ownership back, but giving ownership to its caller. This is potentially a way to move one value from one name to another. Which is exactly what's happening in this line here. Let S3 equals takes and gives back S2. So it's not giving it back to anything. What we did was takes and gives back. We gave ownership of the value inside of S2. We gave ownership to a string. And then a string. Hey, Mystic, how you doing, buddy? Good to see you around. Good to see, and hope you're having a good lunch break. I'm doing okay. I'm starting to see more of the ownership stuff in Rust. And the ownership stuff in Rust is starting to make a little bit more sense. Of like, okay, here's this situation. In fact, I'll go over it real quickly. So we take this variable S1, and then we call gives ownership. So there's nothing inside of S1 as of right now, but then we call gives ownership, and this function gives ownership creates a new variable, which we're calling some string, and then we're returning it. So we return it, and now S1 owns the string that says yours, which is okay. Okay, we're getting somewhere with this. The thing that like I was struggling with is this, that I was struggling with earlier. The concept I was struggling with earlier, which I wasn't streaming, so no one would know this, is there's this concept here. Oh no, stop it. There we go. there's this concept here, which is takes and gives back. We have a variable s2, which is this string hello that we instantiated before, and we give ownership of s2 into takes and gives back. So now the function takes and gives back, the a string takes it, but then it just goes ahead and returns it, which moves the ownership of that hello string into s3. So s2 no longer owns it, s3 owns it. So moving data around, which is not even like, the data is not even physically moving, but the data that like points to it, the names that do all this pointer stuff, I was struggling with a concept similar to that in a proof of concept I was working on a couple weeks ago, which I wasn't streaming and I wasn't talking to anyone about. But it's a neat thing. But I hope you enjoy your boot camp. Hope I'm not distracting you too much, and I appreciate you stopping. But I do appreciate you stopping by. Anyway, takes and gives back. You understood all of that. Awesome. So are you learning Rust, or because ownership is weird? Ownership is like a weird concept. But basically, I guess you can say the quickest way to like give a really quick overview of what ownership is let's say it's right here. Let's just use these two strings. S2. Oh, sounds like you're passing variables around. You kind of are, but in a language like Python, I can say. In a language like Python, I could just say let s4 equals string from hello. And then I could, in theory, in Python, we could say let s5 equal s4. I can kind of do that here, but it is now, because s5 owns that string variable, that string data. If I wanted to then print, and in Rust it's called print line, s4, if I just wanted to print that s4, we can't, because s4 doesn't own that. S4 doesn't own that hello string. Now s5 owns that hello string. Because we've moved that HELLO string text into s5, and s4 can't touch it. It's not allowed to. And that's what ownership is. It's like, it is a much stricter version of like the stuff that's, if you've ever touched C++, if you know like what a private variable or a private function is, it is much more strict and much more enforced inside of Rust, because it actually is enforced. It's like, oh, S5 now owns hello, S4 can't touch it. Fuck you, S4. Get off my lawn. And so that a lot of those principles now still work for S3. Or sorry, a lot of those principles still apply when you're calling functions, because you're moving a variable, you're moving that hello text into the name, which is a string in this case, or some string in the takes ownership case. If I call takes ownership, whatever I give it, I am giving it. That becomes a lot more relevant later for asynchronous stuff. But then, like in here, because the string hello is now owned by the function takes and gives back, the takes and gives back then returns it, which means it is now owned by S3. It is really weird. Something like the difference between let and const in JavaScript. Ooh. So that is more like dealing with immutability. Let and const are more... Man, I wish Jim was here, but he's in the UK. Fucking bongers. Let is an actual variable, and const is a constant, which means no one can touch const. You could print it, which doesn't have to touch it, you just have to look at it. In ownership, you can't even look at it. If you can only even look at it if you have either borrowed it or you own it. Because mutability exists in here too. We can't actually change that. Once S2 exists, we can't change the value. It is not mutable, aka it's immutable. If we wanted to, we could let S2, just comment that out. We could let mutable S2 equals string from hello. And now we can change the value of S2, but we couldn't before because it's immutable. Now probably still could. It's weird. Mutability of certain variables is still a touched upon topic in this, and it's stuff to keep your mind on. You do some quick admin work here, checking on some things. All right, let's get back to the lessons. Get rid of that. Get rid of the comment. Are we still complaining? Okay, main return from function. All right, enjoy your boot camp, Mystic. Let's see. Here is. And once again, if I didn't tell you already, thank you for stopping by. Return from function. Okay. Does it stop complaining now? Unused variable S3. How about we print it? Or instead of that, we'll just put an underscore on it. Takes and give back. There we go. S2's moved into scope for S3. Now, are we still unused variable S1? There. Stop complaining. There it is. So the ownership of a variable follows the same pattern every time. Assigning a value to another variable moves it. When a variable that includes data on the heap goes out of scope, the value will be cleaned up by drop unless ownership of the data has been moved to another variable. While this works, taking ownership and then returning ownership with every function is a bit tedious. What if we want to let a function use a value but not take ownership? It's quite annoying that anything we pass in also needs to be passed back if we want to use it again. We're about to get into borrowing. In addition to any data resulting from the body of the function that we might want to return as well. Rust does let us return multiple values using a tuple. Okay. So now we're defining fn main return tuple. Example. This main function demonstrates that you can return multiple vars we'll just leave it at that. Let S1 equal string from hello. And we let the tuple of S2 and length will calculate length S1. At which point we then print line the length of S2. Nope. S2 is len. I like my shorthand. Don't question it. Calculate length s. So it takes the input s, which has to be a string, and it returns a tuple. Tuple is 2 values. Did I see? Okay, no, I didn't. String and a u size. What's a u size? I forgot that. What's the u size? Rust. The pointer-sized, unsigned integer type. Oh, okay. Literally, how big is something? So we say let length equals s.len. And if we look up returns, oh, you can't see it because chat's there. Hang on, let me hide chat for just a second. Returns the length of this string in bytes, not chars or graphemes. In other words, it might not be what the human considers the length of the string. So this is the actual length in memory. This is the actual size in memory of the string of S. I'll let you guys come back. It's okay. I only hid you for a second. You're back now. Just calm down. We call that as a function. Returns length. It's the length of the string, dumbass. Comma, period. There we go. And then we return s, the tuple that contains s and length. Calculate length is never used. We'd say main return from tuple example. Where's that at? Main return from tuple example. Function with similar name exists. Oh, nope. Main return tuple example. Cargo run. Main function destination damage stack from heap. I go back here. So if I want to try something, there it is. Yep. So I'm using a Vim thing. I'm highlighting main return from tuple example. Where is that defined? I hit GD, and I'm just going to the definition of that function. I love Vim. I love it so much. Anyway, but this is too much ceremony. All of that pomp and circumstance is a lot of work for a concept that should be common. Luckily for us, Rust has a feature for using a value without transferring ownership called references. I think in some... It's interesting that it's saying references and not borrowing. Anyway, we can save all that. And now we're in... Should I put like a text somewhere on screen on the front of the page that says, hey, we're in chapter 5 now? Should I do that? Might be a good idea. Let's see. You know what? I'll just post it in chat. I'll just post it in all 3 of my chats. Oop. Can I not post it in Kick chat? That's weird. I post it, chat. There we go. We're now in chapter 5. The issue with the tuple code in listing 4.5 is that we have to return the string to the calling function, so we can still use the string after the call to calculate length, because the string was moved into calculate length. Instead, we can provide a reference to the string value. A reference is like a pointer, in that it's an address we can follow to access the data stored at that address. That data is owned by some other variable. Unlike a pointer, a reference is guaranteed to point to a valid value in of a particular type or the life of that reference. Okay. Here is how you would define and use a calculate length function that has a reference to an object as a parameter instead of taking ownership of that value. So for now, what I'm going to do is I'm going to cargo new references. Go into that, vim, open, source, main, open all of that. Then we'll back out of here, references. Oh, excuse me. Cargo run. We saw the hello world, so we're having fun now. All right, so we're gonna say let s1 string from hello. Let length is equal to calculate length, and we borrow the value of s1 to do that. And then we print line. The length of s1 is len. At which point we then say fn calculate length, which takes the input of s, which is a borrowed string, and returns a usize. Actually, there we go. And then we return s.len. This function borrows the value references, or borrows the value of the s input to calculate. So length can be calculated without taking ownership. Len gets calculated without giving ownership of s1. Therefore, it does not move out of scope, and also therefore does not get killed or freed once the function returns. So you define, that's how you would define it, that's how you would use it. So first, notice that all the tuple code from the older example is gone. Second, that we pass ampersand s1 into calculate length. And in its definition, we take ampersand string rather than just string. These ampersands represent references, and they allow you to refer to some value without taking ownership of it. Figure 4.5 to fix this concept. So s, we have the pointer to s1, which is, I guess s. I'm gonna assume that the pointer is instantiated on the stack, and then s1 is then, oh yeah. So s is from calculate length. That's this s right here, this guy, and that points to s1, which itself has a pointer, you know, it has the index. We saw this diagram. It's at the length of 5. It's got a capacity 5. And then the pointer, which points to the actual HELLO. So the opposite of referencing by using ampersand is dereferencing. which is accomplished with the dereference operator. We'll see some uses of the dereference operator in Chapter 8 and discuss details of dereferencing in Chapter 15. That'll probably be interesting. So let's take a look at let's take a closer look at the function call. The ampersand S1 syntax lets us create a reference that refers to the value of S1 but does not own it. Because it does not own it, the value it points to will not be dropped when the reference stops being used. Likewise, the signature of the function uses ampersand to indicate that the type of the parameter S is a reference. Let's try to add some explanatory annotations, which I already did. We don't have to do that. But yeah, S goes out of scope, but it does not have ownership. It refers to what it refers to, and so it is not dropped. S is a reference to a thing that we can't see because of the buttons. The scope in which the variable S is valid is the same as any function parameter scope, but the value pointed to by the reference is not dropped when S stops being used because S doesn't have ownership. When functions have references as parameters instead of actual values, we won't need to return the values in order to give back ownership because we never had ownership. We call the action of creating a reference borrowing. As in real life, if a person borrows something, you can borrow it from them. When you're done, you have to give it back. You don't own it. So what happens if we try to modify something we're borrowing? Try the code in 4.6. Spoiler alert, it won't work. So we'll call fn main no borrowing is bad. So we then say let s is equal to string from below. Then we say change the borrowed value of s. At which point, actually I should probably move this down so that it's more congruent with what the lesson is. And then we say fn change some string, which is a borrowed string. And then we say some string pushter world. And then we even have to just say it, and then trouble, character literal may only contain, wait, what? Where's that at? Oh, I forgot. There we go. Fix that up, and some string, changing this to mutable reference mute. Not borrow some string as mutable. So it doesn't like it. So that point is, we'll say, main no borrowing is bad. And it doesn't like these, so what I will do is I will comment those out. I will comment out the actual calling of it. So here, this code is invalid because it tries to modify a value. It doesn't modify a value without owning it. Actually, put that here. And then, there we go. It is not owned because some string is a borrowed string. Hence, ampersand string. Should move that over. There we go. So we annotated that. It's all invalid. We don't like it. Change. Here's the error. And we already saw the error. These variables are immutable by default, so our references. We're not allowed to modify something we have a reference to. But we have mutable references. We can fix code from listing 4.6 to allow us to modify a borrowed value with just a few small tweaks that use instead a mutable reference. So now, main mutable reference example. So we define main mutable reference example, and that is let mutable s equals string from hello. And then we'll do change, and we'll borrow we'll mutably borrow s. Mutably borrow, I guess. It's very interesting. And change some string. And then we're telling the code that it is both mutable, or it is both borrowed, and it is also mutable, and it is a string. What we should expect. So we say some string dot push stir world. Yes. At which point we say print line from a borrowed and mutable string. String, and then we'll... There you go. Print line S. We'll go into cargo run. The length of hello is 5, and hello world from a borrowed and mutable string. Nice. So if something is mutable and you pass it into a function, you have to tell the function that this is both borrowed and it is mutable. Oh, excuse me. Little tired. So mutable references have one big oh, wait. Oh. First we change s to be mute. Then we create a mutable reference with mute s, with borrowed mute s, where we call the change function and update the function signature to accept a mutable reference with some string, which has to be borrowed and mutable string. This makes it very clear that the change function will mutate the value it borrows. So what if we don't say it's mute? Does it say consider changing this to be a mutable variable mute? We cannot borrow. Actually, hang on. Cannot borrow some string is mutable as it is behind a borrowing reference. Okay. Oh, no, hang on. So the data it refers to cannot be borrowed as mutable. So we do have to make sure that it knows it's mutable, it knows it's borrowed, and it knows it's a string. You have to be very explicit. Mutable references have one big restriction. If you have mutable reference to a value, you can have no other references to that value. This code that attempts to create two mutable references to S will fail. So we will then main two mutable refs is bad. And then we say let mute S string from low. And we say let R1 equal borrowed mutable S. And then we say R2 is the same thing. And we say print line R1, R2. That should probably have parentheses around it. Code is invalid because cannot have multiple mutable references. So now we comment that out. Got it. So here's the error. We compile ownership. Mute S. First mutable borrow occurs here. Second mutable borrow. Now, can I? Oh, that's neat. I can comment out the comment. Okay, so R1, can we non-mutably borrow? Cannot borrow S as immutable because it is also borrowed as mutable. Can we borrow it twice? Can we borrow it twice? Ah, okay. So actually, main 2 mutable refs is bad. Let's go into our code, cargo run. Hello, hello. Okay, so we mutably borrow. So we borrow the mutable string twice, but we don't mutably borrow it. But if we try to mutably borrow it, mutable borrow occurs here, and then immutable borrow occurs here. So we can't, can we do it the other way around? Can I immutably borrow it and then mutably borrow it? Cannot borrow S as mutable because it's R also borrowed. Okay. So we'll just give it that. And then we'll just tell the thing, no, this is commented. And then we comment that out. So you can borrow it multiple times, but you can only borrow it immutably once. And if you mutably borrow something once, you cannot keep borrowing it by anything else. Good to know. The error says that the code is invalid because we cannot borrow S as mutable more than once. The first mutable borrow must last until it is used in print line. But between the creation of that mutable reference and its usage, we tried to create another reference, R2, that borrows the same data as R1. The restriction preventing multiple mutable references to the same data at the same time allows for mutation, but in a very controlled fashion. It's something that new restorations struggle with because most languages let you mutate whenever you'd like. The benefit of having this restriction is that we can prevent data races at compile time. A data race is similar to a race condition and happens when these 3 behaviors occur. 2 or more pointers access the same data at the same time. At least one of the pointers is being used to write to the data, and there's no mechanism being used to synchronize access to the data. Okay. So data races cause undefined behavior and can be difficult to diagnose and fix when you're trying to track them down at runtime. Rust prevents this problem by refusing to compile code with data races. As always, we can use curly brackets to create a new scope, allowing for multiple mutable references, just not simultaneous ones. Oh, so if we do fn main multiple scopes allow multiple mutable references. So we say let mute s equals string from below, as always. And then we say, we create a new scope. We let R1 equals a mutable borrow of S. And then R1 goes out of scope here, but since it is borrowed, S still exists. Right? We let R2 equal mutable borrowing of S. If I save it, yeah, it seems to work correctly. Rust enforces a similar rule for combining mutable and immutable references. Code results in an error. But R1 is equal to S, no problem. R2 is equal to S, no problem. And R3 is equal to a mutable borrow of S, which is a big fuck off problem. We save the error, no problem. Immutable borrow occurs here, and then mutable borrow occurs here, and we can't do that, which we already kind of experienced up there. We can't have a mutable reference while we have an immutable one and the same value. So you can only instantiate a mutable borrow once. You can only have one mutable borrow of any kind of data at a time. You can do immutable borrows. You can do all of those all you want. So users of an immutable reference don't expect the value to change suddenly from under them. You can't, no rug pulls here. However, multiple immutable references are allowed because no one who is just reading the data has the ability to affect anyone else's reading of the data. So it's basically, you can't give write access to more than one person, but you can give read access. Note that a reference's scope starts from where it is introduced and continues through the last time that reference is used. For instance, this code will compile because the last usage of immutable references, the immutable references, the print line occurs before the mutable reference is introduced. Let's see. Oh yeah, okay. So we have mutable S is the hello string. We have R1, which is a borrow, R2, which is a borrow, and then we have R1 and R2, which we're printing. And since they won't be used after this point, we can mutably borrow that. Wait. Oh, does it only be... Hang on. I almost missed this. Let me see. Main mutable multiple scopes. All that. And main usage is why multiple mutable borrows are bad. Let S equal that, no. Let that. Let R1 equal borrowing S. Let R2, oh, R3 is mutable borrow of S. Okay, and then we print line R1, R2, R3, and R3. Oh, I need to invoke the macro. So we can't borrow it mutably. Let me print it. Go up there and yeah, get rid of that. And there's no problem here. And if I cut, and so if I go to that cargo run, mutable borrow occurs here at R3. More immutable borrow later used here. So if I didn't use it, hang on. Main usage is why multiple borrows are bad. Hello, hello. from early in the multiple borrow function. Hello from early in. So it's not the fact that we mutably borrow it, it's that it's the actual problem in this code. The actual problem in this print line is the fact that we're trying to use R1 and R2 again after we've created a mutable borrow, which means in theory the mutable borrow could have mutated S, which in turn would mutate R1 and R2. So R1 and R2 expect to read the value, and they don't actually expect this, but you as the programmer expect this, is that since this isn't a mutable borrow, since these two aren't immutable borrows, you expect the value that is borrowed in R1 and R2 to stay the same until they are used by R1 and R2. And in fact, I'll put that in a comment. The actual problem with mutable borrows. Oh, no. Borrows is that we are using the immutable borrows after the mutable one is made, which could introduce change to the supposedly immutable borrow. No. Bad. So then we call message Y. What's our problems here? Unused. I'll just deal with this. Actually, print line R2. That'll get it to shut up. This is intentional. Yeah, let's go ahead and prefix that. So because in this one, in this piece of code, R1 is put within a scope and then pulled out of that scope. That's why R2 is able to mutably borrow it again, because R1 is killed off. It's freed, it's whatever, it's dropped, it's killed, it's whatever language you want to use. Okay. Oh, God. References and borrowing, dangling references. Scopes of the immutable references are 1. Wait, hang on. We also cannot have mutable references while we have immutable. Okay, we've already seen that. The scopes, we've dealt with the scopes problem. Even though borrowing errors may be frustrating at times, remember that it's the Rust compiler pointing out a potential bug early, at compile time rather than at runtime, and showing you exactly where the problem is. Then you don't have to track down why your data isn't doing what you thought it was. So in languages with pointers, it's easy to erroneously create a dangling pointer. A pointer that references location in memory that may have been given to someone else. By freeing some memory while preserving a pointer to that memory in Rust, by contrast, the compiler guarantees that references will never be dangling references. If you have a reference to some data, the compiler will ensure that the data will not go out of scope before the reference to the data does. So the name dies before the value, and that's always the case, is what I'm seeing here. So let's try to create a dangling reference to see how Rust prevents them with a compile time error. All right, so main we'll call this main dingle dangle borrow. Let reference to nothing equals dangle. At which point we say fn dangle takes in a borrowed string, or no, returns a borrowed string. Wait. Huh. So we say let s equal string from low. And then we say return the borrow of s. Consider using static lifetime. Okay, so now we get it. Now we're getting into lifetimes. This error, yeah, the error message refers to a feature we haven't covered yet. So if we cargo run static string, static lifetime, consider using the static lifetime. At which point now we just say, actually, hang on. This code is invalid because it would try to return a borrowed value, but since return a value via borrowing, probably. But since the data is instantiated, this scope, the value is dropped. Therefore, the caller would receive a pointer to thin air. So now I can comment that. Put that in a comment. Okay, the error message refers to a feature we haven't yet covered. We'll discuss lifetimes in detail in chapter 10. But if you disregard the parts about lifetimes, the message does contain the key to why this code is a problem. This function's return type contains a borrowed value, but there is no value for it to be borrowed from. Take a closer look at exactly what's happening at each stage of our dangle code. So we have dangle, should return a borrowed string. We let s equal string from hello. This is a new string. Then we try to return the borrowed s. We return a reference to the string. Here, s goes out of scope and is dropped. Its memory goes away. Danger. So yeah, it's what I wrote. Code's invalid because it would try to return a value to thin air. Because s is created inside a dangle, when the code dangle is finished, s will be deallocated. But when tried to return it to a reference to it, it means this reference would be pointing to an invalid string. No good. Rust won't let us do this. The solution here is to return the string directly. So instead, dangle fn no dangle, which means now we can comment this out. Or no, we don't have to. Fn no dangle takes no input, but it returns a strung. Let s equals string from lr. Earn s. Reference. Comment that. We'll say let reference to something equals no dangle. Print line. Reference to something. Then in hello, from being from being returned as a whole instead of a reference. How do I get that? No dangle is never used. Wait. Oh. Main dingle dangle borrow. So this works without any problems. Ownership is moved out. In fact, let me just prove that works. Hello from being returned as a whole instead of a reference. Bong bong. Works without prop. Ownership is moved out and nothing is deallocated. Let us recap what we've discussed about references. At any given time, you can have either one mutable reference or any number of immutable references, and references must always be valid. Next, we'll take a look at a different kind of reference, slices. I'm going to need to get up, stretch my legs just a little bit. I hope you guys do too. Sorry, I don't have my mic in that, I don't have my audio set up in that scene. I'm going to have to do that real quick. In fact, instead of that, wait, why is, this scene is what I was wanting. Instead of doing that, I'm just going to put the Be Right Back on. I'll have to reconstruct the Be Right Back scene. Just move this over just a little bit. I'm just kind of toying and playing some of my scenes, making sure everything's visible the way I like it. So I will be right back. I'm going to stretch my legs, and pop a few things back into place, and we'll get back to it. Did you miss me? I hope you did. Or maybe I hope you didn't. Who knows? Who really knows it anywhere out there? Either way, I am in fact back. We can move on to the next chapter, which talks about slices. What chapter is this? Oh, we're still in chapter 4. Oh man, so structs to structure-related data, enums and pattern matching. Okay. So we manage growing projects with packages, crates, and modules, collections of data. So we have vectors, UTF-8, storing keys, error handling, traits, and lifetimes. Lifetimes is going to be a fun subject. Then we go into testing. So we build a command line program. And okay, so once we get to chapter 12, they start going into like actual capstone projects. More about cargo, smart pointers. Okay, fearless concurrency. Really? Using threads. Okay. Shared state concurrency, extensible concurrency with async. Object-oriented programming features of Rust. Oh, okay. Could be nice. And advanced features, unsafe Rust, advanced traits, and then the final project, building a multi-threaded web server. That's gonna be weird. But anyway, we're back to the slice type. So, the slice type, where we say slices, let you reference a contiguous sequence of elements in a collection rather than the entire collection. It is a type of reference. It is a kind of reference, so it does not have ownership. Here's a small programming problem. Write a function that takes a string of words separated by spaces and returns the first word it finds in that string. If the function doesn't find a space in the string, the whole string must be one word, so the entire string must be returned. So let's work through how we'd write the signature of this function without using slices to understand the problem that slices will solve. We say that the first word is a string. We say the function first word takes a variable s, which is a borrowed string, and it returns what the fuck? The first word function has a borrowed string as a parameter. We don't want ownership, so this is fine. But what should we return? We don't really have a way to talk about part of a string. However, we could return the index of the end of the word indicated by a space. Let's try that. So let's go out of here, we'll back out, we'll cargo new slice examples. Then, go into here, back out, go back into slice examples, cargo run, we'll open Vim, main, nope, fold, boom. So, then first word, S, is we're borrowing a string. We return a usize. We let bytes equal s.as bytes. And for the tuple of I, the borrowed item, in bytes iterate turns an iterator. Hang on. Okay. It turns an iterator over the slice. Iterator yields all items from start to end. So if we let x is a borrowed vector 1, 2, 4, we let the mutable iterator equal x.iterator, then we assert bytes.iterate.enumerate which creates an iterator, which gives the current iteration count as well as the next value. The iterator returned yields pairs item and I and val, where I is the current index of the iteration and val is the value returned by that iterator. Enumerate keeps its count as a new size. We want to count by a different sized integer. The zip function provides similar functionality. The method does no guarding against overflows, so enumerating more than new size max elements will either produces the wrong result or panics. Okay. So we're going to enumerate. So for all of the values and their indexes, for all of the indexes and the actual values, which we're borrowing the values inside of bytes, iterate, enumerate. Oh, nope. We say if item is equal to the bytes value of the space, we return I. And we return s.length. Or no, we don't return it, but we return it. F main. First word. Hello. Hello world. Arguments to this function are incorrect. Oh, we want to borrow hello world. Arguments to this function are incorrect. What does it say? Mismatch types. Okay, so we can't give it a literal. We actually do have to say let s equal string from hello world. Then we say we borrow it. At which point cargo run. It ran, but it didn't show us anything. Okay, yeah. So if we find a space, we then return the actual iterator that says that. But if we don't find a space, we just return the length of the entire goddamn thing. Okay. So the first word function that returns a byte index value into the string parameter. Because we need to go through the string element by element and check whether a value is a space, we'll convert our string to an array of bytes using the asBytes method. Yeah, and that's exactly what we did. We then create an iterator. We create the iterator over the array of bytes using the iter method. We'll discuss iterators more in detail in 13. For now, know that iterator is a method that returns each element in the collection. It returns each element in a collection, and that enumerate wraps the result of iterator, or iterate, and returns each element as part of a tuple instead, which also includes its index. Okay? The first element of the tuple returned from enumerate is the index, and the second element is a reference to the element. So you know what I'm going to do, just so I'm not... There we go. Return index. Because enumerate method returns a tuple, we can use patterns to destructure that tuple. We'll be discussing patterns more in 6, but in the for loop, specify a pattern has I for the index in the tuple and borrowed item for the single byte in the tuple. Because we get a reference to the item from enumerate, we use borrow in the pattern. Inside the for loop, we search for the byte that represents the space by using the byte literal syntax. If we find a space, we return the position. Otherwise, we return the length of the string using s.length. We now have a way to find out the index of the end of the first word in the string, but there's a problem. We're returning a usize on its own, but it's only a meaningful number in the context of the borrowed string. In other words, because it's a separate value from the string, there's no guarantee that it will still be valid in the future. Consider the program in for8 that uses first word function from listing for7. So we say hello world, we call for s, and then we do s clear. So, well, first we let word, first word, and then we call s.clear. Interesting that it doesn't call drop. Cannot borrow, as it is not declared as mutable. The program compiles without errors. Really? Let word net borrow s is mutable as it is not declared mutable. Oh, it is. We do want it. Okay. Word isn't connected to the statement s at all. Word still contains the value 5. We could use that value 5 with a variable s to try and extract the first word. But this would be a bug because the contents of s have changed since we say 5 in word. Having to worry about the index in word getting out of sync with the data in s is tedious and error prone. Managing these indices is even more brittle if we want to write a second word function. Its signature would have to look like this. We'd have to use usize. Now we're tracking a starting and an ending index, and we have even more values that were calculated from data in a particular state, but aren't tied to that state at all. So, once you've returned the two indexes, which are considered usizes, you've returned the two indexes, but the string can still change. And if the string changes, you're fucked, because those two indexes still exist in memory, and they think they're valid, but they're not because the string changed, and fuck you. Skill issue. So now we're trying to, luckily, Rust has a solution to this problem, string slices. So, fn main slice working example. So we let s equals string from hello world. We say let hello equals. Oh, but then that's actual. Wow, okay. So we let hello is equal to the borrowed s from 0 to 5. So that's 0. That's 0, which is the H, 1 is the E, 2 is the L, 3 is the next L, 4 is the O, because it's 5, because that's referring to a length, not an actual index. So 0 through 5, you starting at index 0 and going for a length of 5? Wait, hang on. But the next one over is 6 to 11. So that's 0, 1, 2, 3, 4, 5. So it would include the space 6, 7, 8, 9, 10, 11. Wait, no? That sounds fucked up because if you're going 0, 1, 2, 3, 4, 5. Wait, no. Oh, okay. length rather than the index inside the string. So you would go to 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's weird notation. That is really weird to me. Because the first number is the actual starting index. So you would expect the second number would either also be an index, or it would be a length. A length of the substring. We call them substrings in Python. I guess we're calling them slices here in Rust. You would expect, or a sublist, a subarray. You would not. This seems to be the starting index the starting index the actual value, the length where you stop in relation to the full string rather than the substring. That's really weird notation. That is weird as hell. Turn the music down just a little bit. I noticed the music's kind of getting in the way. Just a little bit. So rather than a reference to an entire string, hello is a reference to a portion of the string, specified in the extra 0 to 5 bit. We create slices using a range within brackets by specifying starting index ... ending index. That's not the ending index though. It's 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There is no 11. That should be never used. Print line. Hello. No. World. And then we say main slice working example. Cargo run. Hello world. What if I say hello world? 6, 7, 8, 9, 10. Should be 5 characters, but instead, 11. What is, okay, print line s.len. Yeah. Because of this opening brace. Wait, really? Let len equal s.len. $11. There's no 11 index though. That's a length. That's not an index. Oh god. Where starting index is the first position in the slice and ending index is one more than the last. Where starting index is the first position in the slice and ending index is one more than the last position in the slice. So that is how many off by 1 errors are introduced in code because of that. Wow. Okay. Internally, the slice data structure stores the starting position and the length of the slice, which corresponds to ending index minus the starting index. So in the case of let world equal and s borrowed string 611, world would be a slice that contains a pointer to the byte at index 7, index 6 of s with a length value of 5. That's what it is. It's the length you take the... Wow, why wouldn't you just put the length then? So it's from 0 to 5 minus 0. Whereas the world variable is the substring, or is the slice, from index 6 to the index of 11, not to an index. At the index 6, and it goes for 11 minus 6 entries in the string. Wow, that's weird. That's a weird way to think of it. With Rust's ... range syntax, if you want to start at index 0, you can drop the value before the two periods. Start at 0, go to 2. In other words, these are equal. That's just okay. That's just notation. By the same token, if your slice includes the last byte, so from 3 and onward, got it. You can also drop both values. Take a slice of the entire string if you're a fucking madman. String slice range indices must occur at valid UTF character boundaries. If you attempt to create a string slice in the middle of a multi-byte character, your program will exit with an error. For the purposes of introducing string slices, we are assuming ASCII only in this section. So, with this information in mind, let's rewrite first word to return a slice. The type that signifies string slice as written S. Okay. So, wait, where is... There we go. So first word S as bytes. Same thing. If it's a space, return the borrowed value of S, 0 all the way to... Wait. Yes, okay. Is that why? Is that why, so that it works with split? Is that how split actually works and that's the reason they did it? There's a string split, right? Hang on. S split. An iterator substrings is... yep, okay, yeah. That's why it works like that. Because it has to in order for split to work. Well, maybe I'm presuming a lot. Maybe I'm presuming a lot by saying split has to work this way. Hang on just a second, y'all. I just realized I'm gonna have to do something to my mic stand later. But that can wait until another day. Or after stream. So we get the index of the end of the word the same way we get by listing 4 by 7. Return, okay, so then return S, return borrowed S, a slice containing the whole goddamn thing. So we get the index of the first word same way by looking for the first occurrence of a space. When we find a space, we return a string slice using the start of the string and the index of the space as the starting and ending indices. I guess it's also indices, not indices non-inclusive. It's weird to think of indices not inclusive. Anyway, well, first word, string value that is tied to the underlying data. The value is made up of a reference to the starting point of the slice and the number of the elements in the slice. Returning a slice would also work for a second word function. Oh, wait, hang on. We're taking a string literal? We now have a straightforward API that's much harder to mess up because the compiler will ensure the references into the string remain valid. Okay. Remember the bug in the program in listing 4.8? When we got to the index of the first word, but then cleared the string. Excuse me. That code was logically incorrect, but didn't show any immediate errors. The problems would show up later if we kept trying to use the first word index with an empty string. Slices make this bug impossible and let us know we have a problem with our code much sooner. Using the slice version of first word will throw a compile time error. Okay, it's time to do that then. And then if we try to size, has to be a borrowed string. Awesome. Can I put? What? Cannot find I in this scope. Oh, index. Awesome. And then in sclear, we say print line the first word of S is word. I think, yes. We can't borrow S as it's, can't borrow. This is mutable because it's also borrow mutable. Is it because, that is the actual mutability thing. Okay, so if we cargo run, immutable borrow occurs here. Okay, no, it is an immutable borrow. Clear it. You try to clear it because it's a mutable borrow. Yeah. Immutable borrow occurs here. Mutable borrow occurs here. Got it. So recall from the borrowing rules that if we have an immutable reference to something, now also then take a mutable reference. Because clear needs to truncate the string. It needs to be mutable. Okay. String literals as slices. Recall that we talked about string literals being stored inside the binary. Now that we know about slices, we can properly understand string literals. S is equals hello world. The type of S here is a borrowed literal string. It is a slice pointing to that specific point of the binary. This is also why string literals are immutable. Borrowed str is an immutable reference. String slices as parameters, knowing that you can take slices of literals and string values, leads us to one more improvement on the first word, and that's its signature. First word, S string. A more experienced Rustacean would write the signature shown in listing 4.9. Instead, because it allows us to use the same function on both actual borrowed string values and borrowed immutable string slices. We have a string slice, we can pass that directly. So then, Pass that directly. If we have a string, we can pass a slice of the string or a reference to the string. This flexibility takes advantage of dereference coercions, a feature that we will cover. Okay, defining a function to take a string slice instead of a reference to a string makes our API more general and useful without losing any functionality. String slices, as you might imagine, are well. Let me actually read through this. We can't borrow, so we'll call this next one fn main string slice as input. Let my string from hello world. Let word equal first word. We borrow my string. Come on, hit the right key. My 0 through 6. It's actually 0 through 5. God damn it. We let word again equal first word. My string of the whole dang kit and caboodle. So we say first word works on slices of strings. Whether partial or whole. So then we say first word also works on refs to string, which are equivalent. To whole slices of string. Nope. So at which point we say let word equals first word borrow my string. Say first word works on slices of string literals. Wait. Oh, wait. Did it just copy it both? Let my string literal equal hello world. That's what it's asking me to do. Works on string literals, whether partial or whole. At which point we say let word equal first. We borrow my string literal 0 through 6. Then we do that again. But we borrow the whole thing, but we borrow the whole thing. And then just for the funsies, say that. And because string literals are string slices already, this works too without slice syntax. Okay, since they're already... So a string, basically it's saying a string is already a string slice. An entire string. Okay. Other slices. String slices, as you might have mentioned, are specific to strings, but there's more general slice type too. I know what this means, but it's interesting that we're not getting introduced to this. So, it's that. Oh, hello. Where's the problem? Function defined here. Expected reference to us. Oh, did I not change that? Wait. And returns, huh? Second word. Ah, okay, yeah. There we go. Oh. Semicolon. And then come up here. Main. String slices input. And we will put the underscore on all of these. Oh no. There we go. Just to get the compiler to not yell at me. Other slices, so we have that. Main integer array slices. Let A equals 1, 2, 3, 4, 5. Let slice equals borrowed A 1 through 2. And then we say assert equals asserts that two expressions are equal to each other using partial equal. On panic, this macro will print the values of the expressions using their debug reps. Like assert, this macro has a second form where a custom panic message can be provided. Got it. So slice borrowed 2, 3. Main integer array slices. Main cargo run. Hello world 11. Because it's asserted, that is true. This slice has the type borrowed list of 32-bit integers. Same way string slices do, by storing a reference to the first element in a length. We'll use this kind of slice for all sorts of other collections. Discuss these collections in detail when we talk about vectors in Chapter 8. Concepts of ownership, borrowing, and slices ensure memory safety in Rust programs at compile time. The Rust language gives you control over your memory usage in the same way as other systems programming languages, but have the owner of data automatically clean up that data when the owner goes out of scope. Means you don't have to write and debug extra code to get this control. Ownership affects how lots of other parts of Rust work, so let's talk about these concepts further throughout the rest of the book. Move on to Chapter 5 and look at grouping pieces of data together in a struct. Okay. Do we want to try and do Chapter 5? Or do I want to say that it has been a good stream at about 3 hours? I think I can do a little bit of chapter 5, maybe. How long is it? Unit like structs without any fields. Struct. You define the struct. Okay. And then an example program using structs. Uh-huh. Yeah, method syntax. Oh, okay. Oh, that we're getting into impls. I think that's not too bad. We can do two whole chapters in a day. Ugh. Structure similar to tuples. Hang on. How far back do we need to go? Okay. A structure is a custom data type that lets you package together and name multiple related values that make up a meaningful group. If you're familiar with an object-oriented language, a struct is an object's data attributes. In this chapter, we'll compare and contrast tuples with structs to build on what you already know and demonstrate when structs are a better way to group data. I just read that entire paragraph and I didn't take in any of it. Holy shit. Okay, if you're familiar with an object-oriented language, a struct is an object's data attributes. Okay, yeah. In this chapter, we'll compare and contrast tuples with structs to build on what you already know. Okay, so tuples are, yeah, that makes sense. Tuples are going to be similar enough that you might draw that comparison, but they're different enough that you're going to need to know some shit. Demonstrate how to define and instantiate structs, how to define associated functions, especially the kind of associated functions called methods. You know, it's funny, like I had a friend, I was talking about objects, and they said like, oh, well, Rust doesn't have objects. Then why does it have methods? Specify behavior associated with struct type. Structs and enums, discussed in 6, are the building blocks for creating new types in your program's domain to take full advantage of Rust's compile time type checking. All right. Sorry about that. Just readjusted my chair a little bit. So, we define and instantiate structs. Structs are similar enough to tuples that it draws comparison. And we discussed in the tuple type section in that both hold multiple unrelated values. Like tuples, hang on just a second. Sorry about that. The pieces of a struct can be different types. Unlike with tuples, in a struct, you'll name each piece of data so it's clear what the values mean. Adding these names means that structs are more flexible than tuples. You don't have to rely on the order. So it's not unlike a struct to be... I guess you could almost, like... You could say that a struct is kind of like a dictionary. But you have to kind of define your terms before you actually instantiate it. To define a struct, we enter the keyword struct and name the entire struct. A struct's name should describe the significance of the pieces of data being grouped together. Inside the curly brackets, we define the names and types of the pieces of data, which we call fields. For example, here's 5.1. Go ahead and get out of here. Cargo new struct. Get in there. Bim. There. Open that up. Close that. struct examples. Cargo run, compile it. Hello world, hello. All right. So the first thing we have is struct user. I want to know if I have to instantiate it as inside of a scope. I wonder how much scope affects like how structs are defined. Email is going to be a string. Sign in count going to be a 64-bit unsigned integer. Oh, no. No. Stop it. There we go. Struct is never constructed. Dead code on by default. Okay, we'll worry about that in a second. So to use a struct, after we've defined it, we must create an instance. Stating the name of the struct. Okay, so first thing we do is we create let user1 equals a user. And there's that. Active true. Username is going to be string from amp. And then email is going to be string from and amp at amp.amp. No, that's not an actual email address. Fuck off. Oh, no. No such. Not semicolons, commas. Email and sign in count 1. We still want a comma, and we still want semicolon at the end of all of that. Okay. Not that complicated. To get a specific value from the struct, we then say user1 email equals string from not amp at amp.amp. But then we have to instantiate it as a mutable user1. Username are never read. Use dot notation, for example, to access this user's email address, user1.email. We can also change it if it's mutable. Got it. Note that the entire instance must be mutable. Rust doesn't allow us to mark only certain fields as mutable. Ah, okay. With any expression, we have build user, so let's define fn build user. Email string, username string, and it returns a user. User. Active true. Username. Email. So is that cloning? Oh. Sign in count 0. And I'm just going to say return that and give me a semicolon. Shorthand struct initialization. Really? What? Function build user. So then we say build user let user2 email amp2 at amp.amp. And the username will be amp2. It will be a borrowed string literal slice. Does that work? Can I add this in? Oop. To string. That here? Okay. Prefix it with an underscore, user2. That's what I think. The field in it shorthand. Ah, okay. So, username, email. Hang on. Username to string. Missing fields, email. Oh, that's weird. Okay, it makes sense. Okay, let's scroll back up a little bit. It makes sense to name the function parameters with the same name as the struct fields, but having to repeat them is a bit tedious. If the struct had more fields, repeating each name would get even more annoying. Luckily, there's convenient shorthand. So we shorthand that. Let's string. String. We're not borrowing them? We're not. User. Username, email. Function defined here. Try the conversion method. Oh, is it? Can we instantiate that? Ah, yep. So the build user. Let user 2. Instead of, that's weird that it's like using, that's really weird that it's saying, hey, like, let's use, here's this build user example, but we're never actually calling it. So we don't get to see the problems. I guess you're just to kind of expect it to. To string. Converts the given value to a string. Got it. Int to string. User 2 is not ever used, so prefix it. But we'll say, we'll go on with user 3. Let user 3. So creating instances from other instances with struct update syntax. Okay. You say it's often useful to create a new instance of a struct that includes most of the values from another instance, but changes some. You can do this using struct update. So in 5.6, we show how to create a new user. User 2. In my case, it's going to be user 3 without the update syntax. Set a new value for email. Okay, so we have user 2 active, user 1 active. Username is going to be user 1 username. We change the email from whatever it was to another @example.com. Sign-in count is the same. But let's do struct it update syntax. We'll do user 3 equals user. Squirrely. And email is going to be string. It's going to be another amp @example.com. And then everything else from user 1. Comma, remove this comma. Got it. Try the conversion method to string. To string. This is intentional. It is. Give it the prefix. Code listing 5.7 also creates a user2 that has a different value for email. Fields from user1. The ..user1 must come last to specify that any remaining fields should get their values from the corresponding fields in user1. So we can set like a default. Note that the struct update syntax uses equals like an assignment. It's because it moves the data. Oh, are we? Just as we saw in the variables and data interacting with move. In this example, we can no longer use user1 as a whole after creating user2. Can we? Let's try that. Print line user1's email is user1.email. To invoke the macro. Whoops. Cargo run. Not supported in format string. User1.email. Okay. It really didn't like it. It says it looks like it tries to like it, but it doesn't. Fields active, username and sign-in count are never read. Oh, okay. So user1's email. So if we try user1's username. Oh, so user1 still exists, but it just like shatters it and says, okay, you can't use anything except the email because everything else was moved into this new thing. Interesting. Okay. This is weird. We move everything from user1 into user2 except email. User1 is technically still valid, but only the email field. Nothing else. Using tuple structs without named fields to create different types. Okay. Oh, okay. Yeah. That makes sense. So we create structs color. So if we come up here, we can create a struct color and a 32-bit unsigned, another 32-bit unsigned, and another 32-bit unsigned. And these are all going to be RGBs. And we do the same thing for point. Nope, that's not how you spell it. That's not how you spell it. Point. Here we go. Then down here, and we say let black equals color 000. Then we let origin point 000 for X, Y, and Z. But should give these the I don't have to be used sign of shame. So note that the black and origin values are different values because they're instances. Okay, unit-like structures without any fields. Actually, never mind. Let me go back again. God, I feel schizophrenic right now. For example, a function that takes a parameter type of color cannot take a point as an argument, even though both are made up of. Okay, that's mildly important because they're like you would think they're basically the same type because struct up here, struct and point. No. struct and point, from a structure standpoint, are structured in the exact same way. But a point is not a color, and a color is not a point, even though if you were just looking at values in memory, you would see the exact same structure of data. Okay, the unit that we mentioned in tuple type section, these are, okay, you can also define structs that don't have any fields. These are called unit-like structs because they have a similarity to bleh. The unit type that we mentioned in the tuple type section, unit-like structs can be useful when you need to implement a trait on some type, but don't have any data that you want to store in the type itself. We'll discuss traits in Chapter 10. Here's an example of declaring and instantiating a unit struct named alwaysEqual. So struct alwaysEqual, a unit-like struct doesn't need fields. And so we let subject equal always. Prefix it. Prefix it. And we open that up too. Nope, open that. Close that. Instantiating alwaysEqual. To define alwaysEqual, use the struct keyword, the name we want, and then a semicolon. No need for curly brackets. Subject variable. Using the name we defined. Imagine that later we'll implement behavior for this type, such that every instance of alwaysEqual is always equal to every instance of any other type, perhaps to have a known result for testing purposes. We wouldn't need any data to implement that behavior. You'll see in Chapter 10 how to define traits. So ownership of structs. That's interesting. In the user struct definition in listing 5.1, we used the owned string type rather than the slice, literal string slice, borrowed literal string slice. This is a deliberate choice because we want each instance of this struct to own all of its data, and for that data to be valid as long as the entire struct is valid. It's also possible for structs to store references to data owned by something else, but to do so requires the use of lifetimes. Structs to store references to data owned by something else. A Rust feature that we'll discuss in Chapter 10. Lifetimes ensure that the data referenced by a struct is valid for as long as the struct is. Let's say you try to store a reference in a struct without specifying lifetimes, like the following. This won't work. So we have a user. We define the user. The string literals. The compiler will complain that it needs lifetimes. Okay. So then if we give it a lifetime... Oh, we can't give it a lifetime yet because we haven't been taught about lifetimes. So we have an example program using structs. So we have... let width 1 equal 30. And let height 1 equal 50. We print line the area of the rectangle is square pixels. Which is area width 1, height 1. We printed that. And that's in our main. Wait, what? Oh, I have to get rid of that. Yeah. Cannot find function area, so let's define function area. Width, 32. Height, 32. Turns an unsigned 32-bit. We return width times height. Right? So we run that. Area of the rectangle is 1500. That check out 30 times 50? Yes, 1500. Got it. Calculating the area. Now use this for the cargo run. The issue with this code is evident in the signature of area. The area function is supposed to calculate the area of one rectangle, but the function we wrote has 2 parameters. It's not clear anywhere in our program that the parameters are related. It would be more readable and more manageable to group height and width together. So then that means area, we redefine it as dimensions u32 32 and we return dimensions 0 times dimensions 1. Rect1, let rect1 equal 30 and 50. Area of rect1. Nope. Awesome. So in one way, this program is better. Tuples let us add a bit of structure, and we're now passing just one argument. But in another way, this version is less clear. Tuples don't name their elements. Okay. So now, instead of all of that, we redefine it again. We create a struct rectangle, with width, that's going to be a U32, and a height, which is also a U32. Down here, we say let rect1 equals rectangle, which is width of 30, height of 50. Is that valid? Or does it need to be, okay. Width, height. It does need to be explicitly said. So then is area is rectangle. Which is a borrowed rectangle. And it returns a U32. Rectangle width. Nope. Times rectangle height. Yeah? And then we pull that with print line. The area of the rectangle is square can I spell? Can I spell the word square? I'm sorry, ladies and gentlemen. That's deeply shameful. And we borrow rect1. No, we don't put a semicolon there. We put a semicolon here. There it is. So area rectangle, we just did all that, and we compiled 1,500 square pixels. Okay. Here we've defined a struct. So now we go back, width and height are U32. Rect1 is, okay, so what's it trying to teach me here? Print lin Rect1 is Rect1. What is it? Does it not like it? Cannot be formatted with a default formatter. Doesn't implement format display. Okay. Frontline macro can do many kinds of formatting by default. Okay. We continue reading the errors. Here's a helpful note. Display is not in format strings. You may be able to use or for pretty print instead. Let's try it. Printline macro will look like this. Compile the code with this change. We still see an error. Okay, what change are we making? Rect1 is :square question mark. Still doesn't like it. Cannot be formatted using that because it's not implementing because it doesn't implement debug. Where does it say that? I saw it, but I lost it. Debug is not implemented. Rust does include functionality to print out debugging information, but we have to do that explicitly opt into that functionality available for our struct. We add the outer attribute, which is derive debug. Ooh, what's this song? Warm Chocolate Swirls by the Stream Beats crew. This is nice. A little jazzy bit. A little jazzy number. Let's turn that up just a little bit. I'll turn it up for myself too, not just you guys. Just before the struct definition shown in listing 512. Rect1 rectangle. Okay, so then, does it work now? Oh, hello. No, let's... Kinda likes it. Let's see. Rect1 is rectangle with... So it serializes it into these width and height. Now, is that ordered based on... Yes, it is. Okay. If I swap them... Height and width. Got it. Okay. Uh-huh. Wait. So if I go down here, width and height is 30 and 50, but I changed up here height and width, the order of that. Width and height and width. Oh, I don't know what it's trying to do. Okay. So it is running. And we'll see the following output. Nice. It's not the prettiest output, but it shows the values of all the fields for this instance, which would definitely help during debugging. When we have larger structs, it's useful to have output that's a bit easier to read. In those cases, we can use bleh. Instead of bleh, we can put the hash mark in the print line. Ooh, hello. Vintage crown. In this example, using hash will output the following. Oh, so it puts it out in long boy form. Okay, let me try that. So let's print it out in the long boy format. Yeah, see that? It's like the pretty printer. It's like the pretty printer in Python. Another way to print out the values debug format is a debug. The debug macro. Which, oh god. Where's the debug? Which takes ownership of an expression as opposed to printline, which takes a reference. Prints the file and the line number where that debug macro call occurs in your code along with the resultant value of that expression and returns ownership of the value. Calling debug prints to the standard error console stream, standard error, as opposed to println, prints to the standard output console stream. Standard out. We'll talk more about standard error and standard out in the writing error messages. Here's an example where we're interested in the value that gets assigned to the width field, as well as the value of the whole struct in rect1. All right, so let's try, well, we already have debug. So let us try, let scale equal 2. Let rect1 equal rectangle of that, where width is debug of 30 times scale. Height is equal to 50. We expected to see semicolon. Try adding a comma. Oops. Try adding a comma. Oh God. This is it is intentional. Actually, rect2. And then we say debug. We borrow rect2. Not find rect2 in this scope. Oh, because we need to prefix it. Cargo run. So there's our rect1. The source may, so that's the file, that's the line number, which we can verify. Yep, that's the line number. Line 60 is debug 30 scale. And we've debugged underscore rect2 equals rectangle, da 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 da. Height and width, height 50, width 60. Got it. We can see the output, line 10, where the debug expression is 30 times scale. In addition to the debug trait, Rust has provided a number of traits for us to use with the derive attribute that can add useful behavior to our custom types. Behaviors are listed in Appendix C. Partial oh, that's neat. Clone and copy. Our area function is very specific. It only computes the area of rectangles. It would be helpful for this behavior to tie this behavior more closely to our rectangle struct, because it won't work with any other type. Let's look at how we can continue to refactor this code by turning the area function into a method. So we have, oh really? So the struct is the data, and then the impl, which I guess means implement. Rect1 area. That's weird. Why would you? That's weird syntax. Let's change the area function that has a rectangle. So let's see. Actually, I'll just go ahead and, oh no. So dev rust cargo new impl examples. We'll go into impl examples, vim, open the main RS, open that up. Actually, I want to open vim from this instance. But anyway, and in this one, I'm gonna actually quit vim. There we go. Cargo run. At which point, let's go ahead. You know what? I'm just gonna copy this whole thing, and I am going to paste, because good developers write good code, great developers copy good code. So we're telling it that we want to say we want the dibig, and the struct is, here's the data. So width is an unsigned 32-bit, and height is an unsigned 32-bit. But then we say impl. I think it's impl. I don't know. Is it implement? Also rectangle. We also have area self, which should return a U32, which is return that. And then in main, we say rect1 is a rectangle of that height and that width. And then we return that area. We run cargo new again, or cargo run again. 1500 square pixels. Okay, to define the function block, we start an implementation block for rectangle. Everything within this implementation block will be associated with the rectangle type. Then we move the area function within the implementation brackets and change the first, and in this case only, parameter to be self in the signature everywhere within the body. In main, where we called the area function and passed rect1 as an argument, we can instead use method syntax to call the area method on our rectangle instance. So method syntax, I guess, means dot here. The method syntax goes after an instance. We add a dot. Okay, yeah. In the signature for area, we use borrow self instead of rectangle or rectangle. The borrow self is actually short for self, which is borrowed capital self. I guess self is a trait, somehow special, with an implement block. The type self is an alias for the type that the implement block is for. Methods must have a parameter named self of type self for their first parameter. So Rust lets you abbreviate it with only the name self uncapitalized in the first parameter spot. We still need to borrow ourselves. Ladies and gentlemen, that's a philosophical statement for the age. Can you borrow yourself? Or do you have that ability? Is that something you can do? Can you borrow? All right, is there a borrowing of your own soul? Where was I? Okay, we still need to borrow the self to indicate that this method borrows the self instance, just as we did in the rectangle bang rectangle, borrow the rectangle. Methods can take ownership of self, borrow self immutably, as we've done here, or borrow self mutably, just as they can in any parameter. So we chose self here for the same reason we used borrowing rectangle. Borrowed rectangles in the function version. We don't want to take ownership, and we just want to read the data in the struct, not write to it. Want to change the instance that we've called the method on as part of what the method does. We'd use mutably borrow self as the parameter, having a method that takes ownership of the instance by using just self as the parameter is rare. This technique is usually used when the method transforms self into something else. You want to prevent the caller from using the original instance. I've just read all. I can read all that out loud and not take any of it in. I'm so amazed. Okay. If we want to change it, we'd mutably borrow it. Takes ownership of the instance. Having a method that takes ownership of the instance by using just self as the first parameter is rare. Probably because if you take ownership of the self, like, if you take ownership of yourself, you put self inside of a scope, which means then if you exit your own scope, you destroy yourself. I guess there's got to be instances where you'd want to do that. I have to imagine. So yeah, you borrow yourself. So instead, most of the time you're gonna borrow yourself, but in this instance, you're going to be... Or, yeah, you're going to be borrowing yourself most of the time. And then there are going to be occasions where you might want to take full ownership of yourself. Does taking... I guess that's the million-dollar question. If you take ownership of yourself within a certain scope, then does the scope... When you exit the scope, does the self get dropped? Interesting. Okay, this technique is usually used when the method transforms self into something else and you want to prevent the caller. Okay. This technique is usually used when the method transforms self something else and you want to prevent the caller from using the original instance. So you are no longer valid. Whatever the self was is now no longer valid because it has become something different. So I was right. The self, the rectangle, would then... the instance of rectangle would then be dropped because it took ownership of itself to become something different. Okay. The main using for methods instead of functions, in addition to providing method syntax and not having to repeat in every method signature, is for organization. Yeah. We put all things of a type in one implement block. So we have implement rectangle. We say width, and then we borrow the self, which returns bool. Really? Bool? Oh, if it's do we have width? Got it. So self.width greater than 0. But since it's returning a bool, I don't like the syntax where I don't like that Ruby-like syntax. If you're returning, actually fucking return. Tell me you're returning. Don't just say, "Oh, what are you doing with this code?" It's a sentence. It's not a sentence fragment. Ooh, hello. Hey, Sharo. Damn, Sharo's got some good music. Sit here and jam for just a second. I do love me some cassette tape dream. All right, so let's review what I just wrote down. So we can choose to give a method the same name as one of the struct's fields. Okay, so but because you can call it, because you're calling it here, hence the hence the circly bit. But in here, this is not a circly bit, indicating it's data rather than code, rather than things to execute. Choosing as a width to return the value true if the value in the instance's width field is greater than 0, and false if it is 0. In main, when we follow, because it's with parentheses, we know it's a method. Not always when we give a method. Okay, so where's the returns value operator? Wait, what? Two different operators are used for calling methods. You use dot if you're calling a method on the object directly, and if you're calling a method on a pointer to the object and need to dereference the pointer first. In other words, if object is a pointer, object something is similar to Point to in Rust, we don't have an equivalent to that. Has a feature called automatic referencing and dereferencing. Calling methods is one of the few places in Rust that has this behavior. So it works. When you call a method, object.something, Rust automatically adds in borrowing, mutability, or very much not borrowing, so object matches the signature of the method. In other words, the following are the same. P1, so P1.distance that takes a borrowed input of P2. We're actually borrowing P1.instance. The first one looks much cleaner. This automatic referencing behavior works because methods have a clear receiver, the type of self. Okay. So let's say methods with more parameters. Got it. So let's define a couple rectangles. Uh, 3050. This one will be 1040. And this one will be 6045. We're gonna reference them later. We don't... Wait, where's the can hold? Yes, it would look something like the following. Ah. Okay, so let's just see if we can just define can hold. Fn can hold. Which is... Oh, it has to... Wait. Ah ha ha ha. So it would take self, it would borrow self, and then it would also borrow another rectangle. Which would return, let's just define, oh, it would borrow self, and then it would borrow other. We'll call it other, which is a borrowed rectangle, and it returns a bool. So, return, we'll call this other rect, actually. Other rect, whether or not self.area is greater than other rect.area. I think that's right. Can hold is never used, so let's see. Println. Can rect1 hold rect2. Rect1 can hold. And we're borrowing rect2. And we'll just copy it, make it rect3. Awesome. Does that actually work? Can rect1 hold rect2? True. Actually, let's print printing areas. Actually, hang on. Println. Printing areas. Rect1 area. Rect2 area. Free area. Use parentheses to call these methods. That's right. Yep. Oh no. Okay, cool. Well, okay, so strictly speaking, strictly speaking, it's not merely if the area is bigger. Yeah, okay. Width is greater than other. Oh, it actually is. They even said other. So we have area, other rectangle, and we borrow self height over other height. Okay. Which means return, and it's a tuple, which would be self width greater than other rect width and self height greater than other rect height. Strictly speaking. I like it being one line because it goes past my 80th column. I like that. Anyway. Well. If. The math part of my brain is going, yeah, but if the height doesn't work out, you can maybe switch them, and maybe height and width are mismatched, and it can hold that way. But that's not the important lesson here, is it? So can hold self, we borrow self, and then other rectangle. Yep, and we borrow the rectangle, returns a bool. Yeah. So associated functions. All functions defined within an implement block are called associated functions because they are associated, the type named after implement. We can define associated functions that don't have self as their first parameter. These are not methods because they don't need an instance of the type to work with. We've already used one function like this, string from, that's defined on the string type. Associated functions that aren't methods are often used for constructors that will return a new instance of the struct. These are often called new, but new isn't a special name and isn't built into the language. Okay. For example, we could choose to provide an associated function named square that would have one dimension parameter and use that as both width and height, thus making it easier to create a square rectangle rather than having to specify the same value twice. Okay. So function square returns a self. Okay. That's neat. So implement rectangle function square size u32 returns a self, which means it returns a rectangle. I don't know why that seems convoluted. I would prefer to just say it returns a rectangle. But you do you, guys, I guess. Self, width, size, and then we just do the same, but height. Never used. The self keywords in the return type and in the body of the function are aliases for the type that appears after the impl keyword, which in this case is rectangle. To call the associated function, we use the method syntax. Let's square. So we come down here and we say sk is equal to rectangle square, and the size is, I don't know, fucking 30. Area, we already have that implemented. And then we implement a width, other width, multiple implement blocks. Oh, you can, okay. You can just have, hey, I want to define one function for this. And now I just want to define another function for this here, for like organization purposes. Okay. Enums and pattern matching. Are we into chapter 6? Okay, cool. All right. So what are we doing? What's the goal here? I think that's enough to go off of. No, I do not have my audio implemented in that scene, so I'll worry about that later. So I'm gonna see who is... Oh, not... Oh, still wrong scene. Hang on. OBS. There we go. Alright, who actually is live on Twitch period television? Not in following. What's the... Where is the thing? Who is the guy? Software endgame development. Let's see. Movie tracker, QC, 3D space game. Actually, before I do that, let me go ahead and mention I do have a personal Discord. I'll just link it right now, discord.aperture.com. Linking it in the Twitch, the YouTube, and the Kick. If you want to keep track of things I do and weird shit I post, such as pictures of dogs, and sometimes when I'm actually making food rather than ordering DoorDash, I'll just do the weirdest fake Instagram I can and post that stuff up. That's pretty much all I do on there so far. But I'm trying to build something using it, maybe a community, maybe something out of this. You know, I'm trying to be a streamer again. Jesus Christ, what are we doing here? Anyway, so that's that. Who is online? App Hero, yeah, Play Store Paris 40. First game. Oh, a C++ dev. Godot. There's a lot of Godot devs going on here tonight. There's CA2 again. Imperia 4 Dragons. Digital Art. C#. Returning to NeoVim. Okay. Another Vim user. Why not? Let's go. Let's see what he's up to. I'm gonna go ahead and raid this guy. Raid the Dank today. Mostly because the first thing he said was, let's do NeoVim stuff. So let's go see how he's doing, and I hope everybody's having fun, and I hope you all have a good evening. I will see you around.